If you tell me your height, I'll guess your weight. By using a non-Bayesian approach, I'll be confident in my prediction. But my prediction will be wrong. By using a Bayesian approach, I'll be uncertain about my prediction. But my Bayesian prediction may be closer to the true value. What do I mean? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. This tutorial is inspired by a Richard McElraith lecture covering his book, Statistical Rethinking. This tutorial is split into two parts. The first part will cover a non-Bayesian approach to linear regression, and the second part will cover a Bayesian approach to linear regression. In the interest of time, I've prepared some code in advance so we can spend more time going through the Bayesian approach. You can find a copy of my code in my GitHub repository. If you want to follow along, you can save a copy of this code in a tutorial folder on your computer. After you save the file, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square bracket. Activate the tutorial directory. Add the following packages: CSV, data frames, GLM, statsplots, and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. Okay, now that we have our packages loaded, let's download some data. As a motivating example, we'll be using a dataset of human weights and heights collected by Nancy Howell. Howell made these observations in Botswana between the years 1967 and 1969. I'm executing the code to download the data off the internet and to place that data into a data frame. If you're typing this code in manually, you can find a copy of this URL in the description of this video. Click on the Julia logo icon along the left-hand side of VS Code and look for the df variable. Click on the table icon on the right side of that line. This is a dataset with 4 columns for height, weight, age, and gender. The heights are in centimeters, and the weights are in kilograms. This dataset contains 544 rows. If you click on the age column header, that will sort the data by age from youngest to oldest. Clicking on the age header again will sort the data from oldest to youngest. As you can see, there's a wide range of ages. Clicking on the header one more time will return the dataset to its original order. Going back to our code, we only want the data for the adults, which are the individuals that are 18 and older. Click on the Julia logo icon again, and click on the table icon for the df_adult variable. This subset only has 352 rows. And if you click on the age header again, you'll see that the age for this subset now ranges between 18 and 88. Now that we have our data, let's visualize it. A height range of 140 centimeters to 180 centimeters translates to feet and inches to roughly 4'7" to 5'11". Also, a weight range from 35 kilograms to 60 kilograms translates to roughly 77 pounds to 132 pounds. So speaking casually, there appears to be some linear association between weight and height. I'm going to run this plotting recipe again so we can have a second plot showing the exact same data. We'll use the first plot for the non-Bayesian approach, and we'll use the second plot for the Bayesian approach. Okay, now that we've had a look at our data, let's see how to generate a non-Bayesian linear regression model. A non-Bayesian approach to analyzing this data would be to generate a linear regression line using something called the ordinary least squares method, or OLS. Conceptually, OLS draws a line through the data points and then measures the vertical distances between each data point and the line. OLS then squares the distances and then adds them all up. OLS then returns the line that minimizes the sum of the squares of these distances. In Julia, you can define an OLS model by using the glm.jl package. I'm going to go through this section fairly quickly, since this is not a GLM tutorial. I just want to give you a feel for how one might approach this analysis without using Bayesian statistics. In the REPL, you can see the output from GLM. The two numbers that we're interested in are the two values under the coefficient column. The first number is the y-intercept of the line, and the second number is the slope of the line. When using GLM, you can index these values by using the COEF function, short for coefficient, along with an index number. Now that we know the y-intercept and the slope, we can add this line to our plot. We can use an anonymous function to define the function for the line. This line is called the linear regression line. Now that we have an OLS model, we can use it to make predictions. Let's predict the weights for 3 individuals who are not part of the dataset. Their heights are 140 centimeters, 160 centimeters, and 175 centimeters, or 4'7", 5'3", and 5'9". When using GLM, your nu-X data must be in the form of a table data type, like a data frame. You can see the predictions in the REPL. So for the 140 centimeter or 4'7" individual, OLS predicts that their weight is around 36 kilograms, or roughly 79 pounds. For the 160 centimeter or 5'3" individual, OLS predicts that their weight is around 48 kilograms, or roughly 105 pounds. And for the 175 centimeter or 5'9" individual, OLS predicts that their weight is around 58 kilograms, or roughly 128 pounds. If you look at the plot, you'll see that these predictions just come from this linear regression line. Okay, that was an example of a non-Bayesian approach for linear regression. Now, let's take a look at a Bayesian approach. The code for this section is modified code from the personal website of Neil Grantham. There's a link to the original code in the description below. The first thing we need to do for this Bayesian approach is to define our model using the @model macro. For this model, we need prior beliefs for three parameters: the y-intercept of the line, the slope of the line, and a variable for some unknown error. Okay, let's talk about this model. The error represents some unknown factor that may be influencing the outcome. So here we're stating that weight is a function of height plus some unknown factor. These priors are from Richard McElraith's lecture. Selecting the priors is something of an art, combined with some science. For the y-intercept, our initial belief is that it's normally distributed with a mean of 0 and a standard deviation of 10. The thinking behind this prior belief is that if someone has a height of 0 centimeters, then it's logical to conclude that they have a weight of 0 kilograms as well. The standard deviation of 10 means that the y-intercept could be plus or minus 10 if it's within one standard deviation of the mean. This is just an arbitrary number to use as a starting point. Here's what the PDF looks like for a normal distribution with a mean of 0 and a standard deviation of 10. For the slope, our initial belief is that the value could be any value between 0 and 1 with equal probability. A value of 0 means that the line is horizontal. It does seem reasonable that the slope of the line describing the association between weight and height should be some positive number between 0 and 1. Here's what the PDF looks like for a uniform distribution between 0 and 1. For the error, our initial belief is that the value could be any value between 0 and 10 with equal probability. This is an arbitrary distribution to use as a starting point. But it does seem reasonable that the value of the error should be some number greater than 0. But how much greater is unclear without seeing any data. Here's what the PDF looks like for a uniform distribution between 0 and 10. For the likelihood, we have two lines. The line for the average weight is called a deterministic function, since it uses an equal sign as opposed to a tilde. This is just the equation for a straight line. That last line in the model is our belief about the distribution for the likelihood. Recall that the likelihood is the probability of the observations given the parameters. In this example, the observation is the weight for any given height. Our belief here is that the distribution of the weight is normally distributed with a mean value of the average weight and a standard deviation of the error. MV normal is short for multivariate normal distribution. In the distributions.jl package, you can only use single values as arguments in the normal distribution function. But since our data will be in the form of a vector, we need to use the MV normal distribution function. The MV normal distribution function is just like the normal distribution function, but it works for multiple dimensions. Okay, now that we've defined the prior and the likelihood, let's infer the posterior probability. This inference step is essentially the same as the globe tossing experiment from the first episode. We're going to use the no U-turn sampler again, and we're going to draw 1,000 samples from our model. In the summary statistics table, you can see that there are 3 rows for the 3 parameters that we're interested in: the y-intercept, the slope, and the error. If you look at the values under the mean column, you can see that our prior belief was completely wrong for the y-intercept, since we initially thought that it would be some value close to 0. But our prior beliefs for both the slope and the error turned out to be reasonable, since we initially thought that the slope would be some number between 0 and 1, and we thought that the error would be some number between 0 and 10. Although these mean values are interesting, they're really just reference points, since, as Bayesians, we understand the solution to a Bayesian inference is not a number, but a probability distribution. Let's take a look at the details behind the chain to get a better understanding of what's going on. Click on the Julia logo icon and click on the table icon for the chain variable. In this chain, you can see 3 columns for our 3 parameters: the intercept, the slope, and the error. Like we've seen before, this chain contains 1,000 rows for the 1,000 samples. To get a better feel for this chain, let's take a look at Turing's standard diagnostic plots. There are 3 sets of diagnostic plots, one for each parameter. As you can see, the answer to our problem is not a single value, but a probability distribution. The 3 plots along the right side are the posterior probabilities for each of the parameters. These posterior probabilities represent our updated beliefs after seeing the data. Just for reference, I'm going to insert the plots for our prior beliefs, so you can see how our beliefs changed after seeing the data. So how do these updated beliefs translate to our plot with the data points? For that, we can use a for loop to go through each line of the chain and use the values of the parameters to draw 1,000 lines. In addition, we can add a ribbon to show the error to account for some unknown factors. The index for a chain contains 3 values. The first value is the row number. The second value is the column number. So column 1 is the first parameter. And the third value is the chain number. Since we only have one chain, the third value will always be 1 for today's example. In order to see the updated plots, you need to call the name of the plots. As you can see, this plot looks a little different than the non-Bayesian plots. Rather than showing one line for the linear regression, this plot is showing 1,000 lines. The translucent area indicates the error or the unknown factors that may be influencing the weight for any given height. Now, this isn't just some pretty picture. We can use it to make predictions as well. When making predictions using a Bayesian model, the predictions aren't single numbers. Instead, the predictions will be probability distributions, just like everything else in the Bayesian world. Unlike when using GLM, your new X data in Turing doesn't need to be in the form of a table. You can simply use a Julia vector. These new height values are the same values that we used in the GLM example. When using the predict function in Turing, the first argument is your model, and the second argument is the chain. For your model, insert the word missing for the distributions that you're trying to predict. If you look under the summer statistics table, you'll see the predicted mean values for weights 1, 2, and 3. But as good Bayesians, we know that these are merely reference points, so these are not the answers that we seek. click on the Julia logo icon and click on the table icon for the predictions variable. As you can see, the predictions variable is another chain. There's a column for each of the 3 weights, and there are 1,000 rows. So the predict function in Turing went through each row of the chain and made a weight prediction for each of the 3 new heights. Just like any other chain, you can use the plot function to visualize these predictions. The 3 plots along the right side are the PDFs for the 3 predictions. So for the 140 centimeter or 4'7" individual, this model predicts that their weight could be anywhere from 25 kilograms to 50 kilograms, with a higher probability between 35 kilograms and 40 kilograms, or roughly between 77 pounds and 88 pounds. For the 160 centimeter or 5'3" individual, this model predicts that their weight can be anywhere from 35 kilograms to 60 kilograms, with a higher probability around 45 kilograms and 50 kilograms, or roughly between 99 pounds and 110 pounds. And for the 175 centimeter or 5'9" individual, this model predicts that their weight could be anywhere from 45 kilograms to 70 kilograms, with a higher probability between 55 kilograms and 60 kilograms, or roughly between 121 pounds and 132 pounds. Pretty cool, right? Let's take a few minutes to compare and contrast the non-Bayesian approach versus the Bayesian approach. With the non-Bayesian approach, there's only one linear regression line for the dataset. So for any given value of x, there's only one unique value for y. Although this approach is easy to understand and easy to explain, the real world is almost never this simple. This non-Bayesian model implies that if you know someone's height, you can accurately predict their weight. But if you try to use this model to make predictions, your predictions will almost always be wrong. With the Bayesian approach, there's a whole collection of linear regression lines for the dataset. So for any given value of x, there's a whole range of potential values for y. Compared to the non-Bayesian approach, the Bayesian approach is admittedly more difficult to understand and more difficult to explain. But the Bayesian approach is a more humble way to view a world full of uncertainty, while still allowing you to provide some guidance as to where you believe the true values may lie. The Bayesian model acknowledges that if you know someone's height, you won't necessarily be able to predict their weight precisely. Instead, you'll be able to provide a probability distribution around what you believe their weight might be, based on the data that you've seen so far. The Bayesian model also allows you to update your beliefs if you're presented with new data. If you're in the prediction business, the Bayesian approach offers you a more nuanced way of making predictions in an unpredictable world. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!